Hello everyone. My name is Chernam Zamiri, and I'm going to be presenting on the project that me and my colleagues did, which is a loan default prediction. I'm going to be taking you through introduction, background research, and problem problem presentation. So the purpose of our project is to design a predictive prescriptive analytics framework capable of identifying potential loan defaulters um, and optimizing loan approval decisions. The analysis integrates machine learning and mathematical optimization to support data-driven lending strategies that balance profitability, risk exposure, and regulatory compliance. Um, the framework begins with a predictive model that assigns a probability of default to each applicant based on relevant financial and demographic features. The choice of interpretable, interpretable statistical models ensures transparency, regulatory compliance, and clear communication to stakeholders. On our prescriptive model, this risk estimates these risk estimates serve as key inputs into the prescriptive optimization model, which determines the optimal loan approval strategy. The prescriptive model balances profitability with real-world constraints, such as capital limits and acceptable aggregate risk levels. By integrating prediction with optimization, the framework moves beyond risk assessment toward actionable profit maximizing decision making. Taken together, this combined analytics pipeline delivers a comprehensive, operationally feasible decision support tool that strengthens credit allocation, reduces exposure to bad loans, and enhances overall lending profitability. So modern lending institutions increasingly rely on advanced analytics to evaluate borrower risk and guide loan approval decisions. Traditionally, credit scoring models have used linear statistical techniques, most notably logistic regression, uh, because of their interpretability and ease of deployment. This foundation was established in Wigginton 1980. One of the earliest studies demonstrating the effectiveness of logistic regression for credit scoring and setting the standard of transparent credit risk modeling. Uh, More recently, decision trees, ensemble models, and various machine learning techniques have gained prominence for their ability to detect nonlinearities and complex interactions in borrower behavior. Uh, However, as highlighted in Beson's, increased predictive power often comes at the expense of interpretability, creating challenges for explainability, stakeholder transparency, and regulatory compliance. This tension is especially critical in credit decisioning, where institutions must be able to justify model outputs to auditors, uh, regulators, and customers. Uh, so our project mainly focused on predictive and prescriptive uh, modules. So this project situates itself at the intersection of these two domains: predictive modeling to estimate borrower default risk, and prescriptive optimization to select the most profitable loan portfolio under operational and regulatory constraints. Uh, by combining interpretable credit scoring with MILP-based decision organ optimization, the system delivers transparent, data-driven insights and support responsible and profitable lending. Lending institutions face two central challenges: accurately predicting default risk, especially in imbalanced datasets where defaults are rare, optimally allocating limited capital across a set of applicants with varying risk levels and expected returns. Traditionally, prediction-only systems do not directly account for business constraints such as capital budgets, maximum allowable default rates, or regulatory interest ceilings. As a result, institutions may approve loans that meet creditworthiness criteria but do not align with overall portfolio objectives. Um, Predictive component. Um, this develops an interpretable model that reliably estimates the default um, probability of each applicant. And the prescriptive component uses use these probabilities to design an optimization model that maximizes expected profit while satisfying budget risk tolerance and regulatory constraints. This dual approach ensures that lending decisions are not only risk aware but also strategically aligned with organizational goals.
For specification and design of our predictive model, we began by evaluating two interpretable options. These are logistic regression and regression trees. Logistic regression trees because they offer a simple, rule-based explanations, but also along the way we discovered that the regression tree became too deep and it showed a high risk of overfitting. To meet our interpretability and stability requirements, we ultimately chose logistic regression. This is because it handles class imbalance well and provides coefficient-based explanations for how each predictor contributes to default risk. In line with this, we dummy encoded all our categorical variables and removed statistically insignificant predictors. We also tuned the classification thresholds to match different business risk preferences. To prevent overfitting, we used an 80 to 20 train test split and selected a model family with more favorable bias variance trade-off. After we predicted each borrower's default probability, we fed those probabilities into our optimization models. The goal with this was very simple, which was to approve a combination of loans that gives the highest expected profit while staying within real lending cost rates. Our objective function during this optimization was to maximize expected profit, where each approved loan contributes. Our expected objective function was to maximize expected profit. And so to do this, we used three realistic constraints. These were a budget limit based on loan to deposit ratio, a risk limit for the overall portfolio default rate, and an interest rate cap reflected in regulatory rules. From the sensitivity analysis that we did, we found that the risk limit wasn't binding, and the model naturally selected safer loans. However, the budget constraint was binding in this case, meaning the profitability mainly depended on how much capital the lender was willing to allocate. Overall, the optimization stage used the prediction risk to choose the most profitable and realistic loan portfolio. For our data acquisition, we used the loan default prediction dataset from Kaggle, which contains detailed borrower and loan characteristics needed for the predictive component of this project. For the optimization component, not for the predictive model, we generated a synthetic dataset of about 1,000 loan applications in Python. For the purpose of the synthetic data was to create diverse combinations of categorical variables so that the optimization model could evaluate a wide range of possible loan scenarios. This synthetic data was never used for training or evaluating the logistic regression. It was purely used during the optimization stage. On to the descriptive results. So to better understand our data, we carried out several analyses just so that we could get a snapshot of different characteristics of our data. And so once we did that analysis, we discovered that borrowers ranged from the age of 18 up to 70. This showed a mix of new and experienced credit users. Incomes ranged from around $15,000 to about $150,000, and loan amounts spanned from a couple $1,000s to all the way to about $250,000. Our analysis extended to categorical variables such as education, employment type, marital status, mortgage, dependence, and loan purpose. And this analysis, as you can see, is well balanced. The analysis gives a picture that's well balanced, which means we had a very good representation across different borrower groups. We also analyzed credit-related variables, and they also showed broad variation. For example, credit scores range from about 300 to 850, interest rates from about 2 to 25%, and debt to income ratios typically fell between 0.2 and 0.6. These are just measures of central tendencies which also help us understand the data better. One of the most important findings was that defaults were much less than non-defaults, which mirrors real-world lending, which is why credit systems work in the first place. This imbalance highlights the importance of using predictive models to identify the minority of loans that are likely to default. We also took a look at the data quality, and numerical features showed a wide variability without extreme outliers. After our correlation analysis, we discovered that there were very weak relationships. There was not too much correlation, which means that each of the variables that were left after removing the statistically insignificant variables contributes to the model, and no one variable could explain the default rate in this case. For our data transformations, our main goal was to prepare the variables so that the logistic regression model could interpret them correctly. Because our target variable is categorical, we didn't need to do any transformations related to normality or anything like that. Also, of note is that in a logistic regression, doesn't require scaling or normalization, and but we did have to convert the categorical variables into factors and diamond encoded them to avoid collinearity and to ensure coefficient interpretation. So those are some transformations that that we did. Also, we had to explicitly set the reference level for each categorical variable so that comparisons would be consistent and meaningful.
Hi, my name is Etuk, and I will be presenting the results and conclusions. So we kick off with hyperparameter tuning. The hyperparameter for our model is a threshold. It serves as a cutoff above which a loan is classified as a default. We started with a threshold of 0.5, and it's worth mentioning that in lending, this is actually infeasible. It assumes equal cost of misclassifying defaults and non-defaults. Different thresholds values were selected, and different metrics were computed at each of the thresholds to find an optimal threshold. Some of the computed metrics were F1 score, sensitivity, accuracy, but however, sensitivity was selected due to the high cost associated with misclassifying a default. Lending, missing a default, which is a false negative, is far more costly than incorrectly flagging a non-default, which is a false positive. In essence, we are particular about how our model does in terms of false negatives. Sensitivity, also called recall, measures our model's ability to correctly identify actual defaults, which are true positives, and is able to quantify false negatives misclassified by our model. As a complementary metric, the F1 score was selected to serve as a tiebreaker for thresholds that had relatively similar sensitivities. On its own, the F1 metric balances precision and recall and is the metric used in imbalanced data sets like ours. Precision, on the other hand, measures the proportion of defaults that actually default from our model's predictions. So, in conclusion, sensitivity was prioritized because of the cost of missed defaults outweighs the cost of false positives. F1 score is used as a secondary check to differentiate between thresholds that have similar sensitivity. This is an overview of the confusion matrix and associated metrics of our selected threshold of 0.1. It was the best performing threshold in terms of sensitivity. Look at the summary of the confusion matrix. Our model was able to correctly classify 4,411 defaults and missed 8,519, resulting in a sensitivity of 74.4%, which indicates a strong ability to catch defaults. Higher sensitivity means fewer missed defaults, and these aligns with our lending goal, but also comes with a trade-off of lower precision. However, a lower precision is accepted because false positives, which is misclassifying a non-default, will only trigger a manual review and not financial loss. So selecting a threshold of 0.1 prioritizes risk mitigation over operational efficiency. In addition to the confusion matrix, AEC was used to evaluate model performance. AEC evaluates model performances across all possible thresholds and is reliable for making tuning decisions. It is a threshold independent metric, so it evaluates the model's ranking ability before a cutoff is selected. AEC ranges from 0.5, which is as good as random guessing, to 1.0, which infers perfect class separation by a model. Our model had an AUC of 0.426, again indicating strong discriminatory power. Optimization. Each loan application from our synthetic data set was assigned a probability of default by a model. These probabilities guided the decision to either reject or accept a loan. In the optimization simulation, arbitrary values were given to our constraints and average industry values, and the details of these are in the table on the slide. $10 million was assumed to be available for capital. And in the real world, interest rate ceiling is a non-negotiable regulatory constraint, so the sensitivity analysis was only carried out on the budget and portfolio default rates. Optimization results show that default rate constraint isn't binding, as changes in allowable default rate don't affect profits. Loan approvals go through two filtering levels. First, our model filters out potential bad loans that could lead to default. Then the optimization process selects a subset of profitable loans from those that pass the initial filter. This results in lower risk loans being approved, and the threshold for allowable default rate is never reached or exceeded. However, the budget constraint is binding. Increasing the loan to deposit ratio LDR directly raises approved loans, which increases profits. Profits increase by about 10,825 for every 1% increase in LDR, making capital availability the primary driver of profitability. Integrated standpoint, the impact of the selected threshold of 0.1 reduces overall accuracy because more non-defaults are flagged as defaults, but it substantially improves the ability to identify true defaulters. This trade-off is desirable because missing a default carries much higher financial cost than incorrectly flagging a safe borrower. At the constraint level, the budget is the chief driver of profitability. It turns out there's no optimal LDR, and selecting a high LDR would lead to increased profitability. But there's a trade-off as it also leads to reduced liquidity. So the recommendation would be to use a threshold of 0.1 and adopt the average industry LDR of 85%. In addition to the earlier recommendations, we also suggest that our model be used to create a risk-based approval policy where if the predicted probability of default is less than 10%, the loan is approved. If greater than 10%, the loan is either flagged for manual review or for rejection. This is a simple, transparent, and easy to communicate way of loan approval. The impact is that it will capture more true defaulters and it supports safer lending decisions. However, there's going to be increased operational load due to increased manual reviews where non-defaulters are flagged as defaulters, but the cost of such is lower than the cost of missing an actual default. Deployment of this model, we recommend that a pilot test be carried out on one lending cycle to assess real-world outcomes with minimal disruption. A number of things will be closely monitored during the pilot, some of which are changes in approval volume and portfolio mix, number of manual reviews triggered, actual versus predicted default rates. After the pilot, if too many defaults are missed, the threshold should be lowered further. If operational load gets too high, the threshold should be raised slightly. LDR will be reassessed if liquidity or profitability deviates from these projections. Adopting this integrated predictive prescriptive framework will result in smarter, more profitable, and reasonable lending. Thank you.